Okay, good evening. My name is Anil Yadav and I am here to take the sixth tutorial of fundamentals and semiconductor devices. So today we will start with the Schottky Junction. So or we can say Metal-Semiconductor Junction. So Metal-Semiconductor Junction forms Schottky Junction. So after that it comes with what type of the junction it is, like if it is a barrier it is forming, so then it will be a Schottky barrier. Or if the current is flowing smoothly through the junction, then it is a ohmic contact. Okay, so we will start with the what are the properties of the material, like uh, in the band gap. So you can see this is okay, just give me a minute. So okay, so this is the electron energy. Okay, why it is not working? Okay, just a minute. Okay, it is not working. Okay, yeah, now I think it will work. Yeah, so this is the, I think someone wants to join. Just a minute. Yeah. Okay. Okay, so here this is the semiconductor. Okay, I don't know what is happening. Okay, this is the semiconductor. So in semiconductor there is conduction band, there is valence band, and the Fermi level. So this is an n-type semiconductor. As you can see, this Fermi level is closer to the conduction band, so this difference is lesser than this difference. So this is closer to the conduction band, and that's why this is a kind of a n-type semiconductor. So and in a semiconductor, this is the vacuum level. So what is a vacuum level? And so we will see the terms in this one. So this is the valence band. So this is the electron energy upside. So what is a so what is the like vacuum level? Vacuum level is nothing but I at which the electron energy is zero. So when we give when we take out an electron from a semiconductor, so if it is not pulling towards the atom or towards there is no potential pull. There is no potential pull at the electron for the electron at this position. There will be potential will be zero, and the kinetic energy will also be zero. So just understand, this is a semiconductor. So when we shine the light of energy h nu, so the electron is from the valency band gets excited to the conduction band. So what if the energy that we are giving, this h nu, this is much more than that it crosses it exactly can go to the vacuum level. So how so this is the energy that we are giving, the h nu. Okay, what will happen is, so there will be no pull from the semiconductor, that it can just we can knock off the electron from the semiconductor. Okay, this is the thing. So if the h nu is much greater than this is the ionization energy, we call it the ionization energy. If the energy that we are giving from outside, that is greater than the ionization energy, so what will happen is it will get knock off, as well as it will get some kinetic energy. It will move freely above this vacuum level. This electron is free to move. it is completely free to move. It is not in the bound state with the semiconductor. It is not in the semiconductor anymore. Okay, so there are terms like ionization energy, work function, and electron affinity. What is the ionization energy? Ionization energy is the energy when we take out an electron from the valency shell. Okay, from the when it is in the ground state, when the atom is in the ground state, when we take an electron out of that, so that is the which is completely free. Okay, so this is the ionization energy. And work function is the energy difference between the vacuum level and the this Fermi level. Okay, and this electron affinity is what is the energy it will release when we put an electron to the conduction band, to the bottom of the conduction band. Okay, so because EV in a semiconductor, the electron is semiconductor is full of electrons till the electron this EV this valency band will be full with the electrons, but there is no empty state at the ground state. Okay, there is no empty state in the valency band at the ground state, but the energy state that will be empty is at the conduction band. Okay, so whatever electrons that we give from the outside will first will go to the conduction band. Okay, so this is the energy released by the system. So when we give an electron, this is known as the electron affinity. Okay, so now so in a semiconductor, okay, I think I just want to clear this thing. So in a semiconductor there are some material properties. What material properties are? Those which are not changing whatever we do from the outside. Okay, whatever we do from outside, they are the material properties. So electron affinity will be constant. Whatever we do for intrinsic, extrinsic, it will always be constant. But so and this ionization energy will always be constant. So what I want to say is the difference between this vacuum level and this conduction band, bottom of the conduction band, will always be constant. Okay, it is not going to change whether we are providing light from the external, whether it is making any contact with any other semiconductor or metal, whatever. So there will be no change in this gap. This gap will always be constant. Okay, this gap, if however this conduction band bends, may like this. So however this vacuum level will follow this conduction band. Okay, so this gap will always be constant. So the electron affinity will always be constant, whether it is in contact, not in contact, whatever. So whether we are doping, there is a variable doping, so this gap will be constant. And this valency band always the gap between the valency band and this uppermost level of the valency band and the vacuum level, this will always be constant. Okay, these two are the material properties. They won't change whatever we do. Okay, so and another thing is this Fermi level. So Fermi level changes as we dope the semiconductor. Fermi level changes as we apply the bias. Fermi level changes. Okay, Fermi level can move up and down as we dope the semiconductor. So this is not a material property. Okay, so electron. Okay, so this is about the property of the semiconductor. What is the electron affinity and this? So okay, so I think this is the okay. So whenever the electron is in this region, okay, this region is full of states. Okay, full of the empty states. This above the conduction band, there are empty states that are very close. We can say the continuum of the states. So electron is free to move inside the semiconductor, but above this vacuum level, electron is free in the space. Okay, free in the space, we are just knocking out an electron from the piece of the semiconductor. Okay, so if you have any doubt, you can ask me in between also. You just stop me if you don't understand the things. This is a very important thing actually, because metal semiconductor junction is everywhere. Whenever we make the device, wherever there is device, we need to take out the contact from the semiconductor. Where if this is a PN junction, this is a PN junction. Okay, so we need to put a metal over this here, and we need to take out the contact. So this is just I am showing a cross sectional view kind of thing. So but it is not like that. This is P type, this is N type. It is not like that. When we fabricate it, it is a completely a different kind of structure. But I am just showing you this thing. So we put in the metal just because to make it equipotential, so that if we put here, so there will be a kind of current grounding kind of thing. So there will be a more resistance. Sometimes it will be less resistant, or there are so many things. Okay, so we put contacts. So it is very necessary to see whether it is what type of the contact it is making. So if it is blocking the current, if it is come smoothly, if the current is flowing very smoothly in between the metal and the semiconductor, how it is flowing. So it is very important for the device purpose to understand the basics of the metal semiconductor junction. Okay, so if you understand these things, these three things, this ionization energy, work function, and electron affinity, you can solve the how the junction will behave if it is ohmic contact or the Schottky barrier. So you can with these three things you can just check how this behave. So mainly the main part is the work function only. So we will see how it behaves. Okay, so this is a metal, a piece of metal this side, and this is a piece of the semiconductor. Okay, so these are the isolated in the sense this is the piece of metal and different, we have not joined them yet. Okay, so the difference between the vacuum level and the Fermi level is the work function of the metal. So there is no band gap in a metal, because metal there is abundance of the empty states just above the Fermi level. Okay, so that's why this is a good conductor, because electrons can easily go easily. These are the free electrons, these are the available states for the electrons. So electron is free to move inside a semiconductor. Okay, so there is no band gap in a metal, not a semiconductor, in a metal. Okay, so this difference between the Fermi level, the uppermost level till it is filled at 0 Kelvin, we can say at 0 Kelvin it is filled up to the vacuum level. So vacuum level, so the energy required to knock off an electron from this level to the to make it completely free, or where the kinetic energy and potential energy is zero. At this point, at this level, the kinetic energy of the electron is equal to zero, and potential energy will also be zero at this point. Okay, so electron at this point is not moving anywhere, but it is free. Okay, so as we say, from the gravitational pull of the of earth, we can say you can have an analogy. So from gravitational pull, so we throw an stone or something with the escape velocity, so that it can go out of the pull of this earth. Okay, so where the kinetic energy will always be zero, and the potential energy will also be zero. Okay, so this is the work function of this metal. Okay, so now so as I already told you, this is the electron affinity, and this is the work function of the metal. So if now what will happen if this metal will we will join this metal and the semiconductor, what will happen? So this is the Fermi level, and this is the Fermi level of the semiconductor, this is the Fermi level of the metal. What will happen when we join them? So okay, so this is the thing, this is the diagram when we join them together. What will happen now? What will happen? What can happen? So if the Fermi level, so this vacuum level will align. So let us what sort of the possibilities can happen when we join a metal and a semiconductor? What is the possibility? Just forget about the Fermi level now. For now, just forget about the Fermi level. Okay, what will happen when we join them, and this what are the things that can align? Just suppose this vacuum level of both the metal and the semiconductor are aligning. So what things cannot change is this electron affinity. Okay, this cannot change. So at this position, so this work function, so at this position, this Fermi, this is the work function of the semiconductor. Now we can see the Fermi level, there is a gap between the Fermi level. Okay, there is a gap between the Fermi level of the metal and the semiconductor. So if the Fermi level is not constant throughout the metal semiconductor junction, then what will happen? There is a current flowing in them at that. So if if there is a difference between the delta EF is there, delta EF is not equal to 0, then there is a current. J is not equal to 0, then there is current. So but at equilibrium the current should be 0. Okay, so this cannot happen ki we just align the these vacuum levels. Okay, there must be current flowing. Okay, without any application of the potential. Okay, without any application of the potential, that cannot happen, the current cannot flow. Okay, so Fermi levels must align, because current is 0. Okay, Fermi levels must align. So now let's align the Fermi levels of both the metal and the semiconductor. So this is metal's Fermi level, this is the semiconductor Fermi level. Now Fermi levels are aligned, but we haven't taken care of the vacuum level and other things, this conduction band and the valency band. We just aligned the Fermi levels. So what is the thing is, so if I am knocking off an electron from here, just a minute, someone wants to join. Okay. Yeah. So what will happen if we have just aligned the Fermi levels? Okay, we just aligned the Fermi levels of the metal, but okay, just suppose we have knocked off an electron from the metal, from at this position to the vacuum level. We just give an energy which is equal to the phi m. Okay, so the electron is here, which is moving here at this position, so which has the kinetic energy is 0 at this edge. If this electron is at this edge at this point, it has the zero energy. But according to this side, if the electron comes at this location, so it has non-zero kinetic energy, it suddenly gets an kinetic energy. That cannot happen. Okay, from at this side of the to the semiconductor side of the junction, so the electron has some kinetic energy. It is completely free from the piece of the semiconductor and the metal. It is free, but at this position it is there just free. Okay, it is not completely free, but it is just free at this location. The kinetic energy is zero, but at this towards this side, the kinetic energy is not zero. Okay, so so the okay, if that electron crosses the interface, so it has a non-zero kinetic energy. That cannot happen actually. So this, because we can see or we can say kinetic energy, the change in the kinetic energy here is the delta. Kinetic energy is delta E is the kinetic energy. So kinetic energy, the change in kinetic energy is E. That too in very, so that this is the microscopic gap which is in angstroms. Okay, so at very small change in the distance displacement FDR. Okay, this dr, very small change in the displacement, we can say this is the delta is the microscopic gap at the semiconductor metal interface. Okay, this f delta will be too high. Okay, so that cannot happen. That will be, can say this is close to the infinity. That cannot happen. Okay, so this vacuum level should be continuous. At this point there should be a the point, this should be constant. This Fermi level should be constant throughout the metal semiconductor interface or so at equilibrium. But this vacuum level should also be continuous. So this vacuum level should start at this position, should start either, it should go this cannot happen as we have already seen, but this should be continuous, so that there should not be, the change in the kinetic energy should not be infinity. Okay, so should not be more than zero, we can say. Okay, so it should come like this, okay. So, and another thing here we will see. So this is the kind of the ideal Schottky junction, which is metal semiconductor junction. Okay, so what will happen? So in this one, so on the side of the metal it is constant. Now here it is changing. Okay, so as we have seen, it should be continuous, so it is continuous. Okay, and Fermi level is also aligned. Okay, so the current is zero and this is also continuous. And another thing, as we have seen, electron affinity. This electron affinity and this ionization energy, both should be constant throughout the semiconductor. Okay, both should be constant. So if it is following this kind of trajectory, not trajectory, if it is kind of bending, the bending of this vacuum level is like this. So this conduction band and the valency band should also follow the same. Okay, so how it will be look like, so that we have already seen in the PN junction. Okay, in PN junction we have calculated the, from the Poisson's equation we have calculated the electric field. First we have calculated the electric field, and then from there we calculated the potential. Okay, we calculated the potential. This is nothing but the potential. Okay, the energy minus of QE. Okay, that is the potential. V is equal to, I think, minus 1 by QE or 1 QE something. This is the kind of relation. Okay, this is the kind of relation which is just opposite to the potential that we have already calculated from the Poisson's equation. Okay, so this is how the bands will bend at the semiconductor metal semiconductor interface. So here that we have assumed, in this case we have assumed that the Fermi level, this work function of the metal was more, phi m was greater than phi s. Okay, that we have assumed. So it can be other way around also. So phi m can be less than phi s, that we will see once. Okay. So in this case, as okay. Okay, I'll write something. So no, okay, in this case, so if the Fermi level is higher, Fermi level is less in the semiconductor, so electron energies are higher in the semiconductor. Okay, if phi s is less than phi m, so at this case, so this direction is nothing but electron energy. Okay, electron energies are higher in the semiconductor, so the electrons will transfer from the semiconductor to the metal. Okay, so electrons will transfer from the semiconductor to the metal, and they will leave behind the positive Nd plus here. The ionized, as we have doped the semiconductor with the donor impurities, as it is a n-type semiconductor, so it will ionize to Nd plus plus electron. The donor impurity will ionize. So these are the ionized atoms that we will be left behind. Okay, so at this position there are Nd plus, electrons are moved, the free electrons are moved from the metal, from the semiconductor to the metal. So there is a deficiency of the electrons. So this is the depletion, as there are no mobile charge carriers in this region, so there will be this region will deplete. Okay, this region will deplete, and electrons will transfer from the semiconductor to the metal. So there will be, that's why there is a band bending. Okay, that's why there is a band bending at this, because, and as there are less number of electrons in this region, so that we can also see from the Fermi, the gap between the conduction band and the Fermi is also increased. So from this we can see that there is less number of electrons, okay, which are transferred from the semiconductor to the metal. Okay, so, and another thing that we have seen in the PN junction, that was the built-in potential. Okay, this the extent of bending, this extent of bending is nothing but the but the built-in potential when a semiconductor metal junction forms. Okay, this is the QVBI. Okay, and another thing is, so some of the electrons are already transferred till the energies of the electrons reaches to the same level. Okay, so electron energy reaches to the same level, or we can say the Fermi level reaches to the same level. Until then, there will be transfer of the electrons from the semiconductor to the metal. So now so and in this region we can also see. Okay, and another thing is in this region there is a no difference. This Fermi level is the difference between the Fermi level and the conduction band is constant, or there is no slope in the conduction band. Okay, the conduction band is constant, the valency band is constant, so there is no field is not there. So in this region there is a slope, or there is slope in the conduction band and the valency band, so there will be a field. Okay, so that we have already seen in the PN junction. Okay, there will be a field. So if we put an electron here, that will roll down in this side, so the field will be opposite to the electrons. Okay, opposite to the flow of the electron. Okay, so another thing that I want to tell you is one more thing. that we haven't seen is, so the barrier. Okay, a barrier that we can introduce in the next slide also. And so what is the built-in potential that we can see? The built-in potential will be okay, I haven't, okay, that we can see. Okay, whatever the bending here is followed by the this vacuum level also. Okay, this bending, so how much bends will bend, so that is we can see from the work function of the metal and the work function of the semiconductor. Okay, this, okay, so that we can see in this one also, that we can see. So this much of the the Fermi level will move until it is aligned with this, both the Fermi levels will align. So this Fermi level will go down to match with the metal Fermi level. Okay, so how much this will move? This will move the difference between the work functions of the metal and the semiconductor. Okay, this is the work function of the metal and this is the work function of the semiconductor. So how much is the difference? Phi m minus phi s. Okay, this is the difference. The difference will be equal to the built-in potential or built-in voltage. Okay, so this QVBI is equal to phi m minus phi s. And how much it will be? And how much it will be? Phi m minus phi s. Okay, so and now we need to calculate it. Phi m minus and phi s is equal to okay, this, okay, this is the electron affinity. Okay, phi s is equal to electron affinity chi s plus this, the difference between the conduction band and the Fermi level, and this difference can be calculated from the doping. The extent of doping we have already done. Okay, that we have done in the semiconductor, how much our semiconductor is doped. So that we can, this difference q phi c is the difference, the potential difference between the potential energy difference between the this conduction band and the Fermi level. So this Fermi, so that we can calculate from the doping. So which is given by the kT by Q ln Nc by Nd. Okay, so this Nd is the doping of the semiconductor, so this is given by that thing. So now we can easily calculate the built-in potential. Okay, so if you have any doubt, you can ask me in between, and we can further solve these equations. Okay, so actually these are already done. This is already done in the PN junction. Okay, so so let us say this is in the equilibrium. So whenever an electron, if there is an electron which wants to come towards the semiconductor side, it has to jump over this barrier phi b. Okay, this phi b is the barrier. Whenever there is an electron that wants to come from the metal to the semiconductor, so this is the injection barrier we call. Okay, this is the injection barrier, and this is important when we are trying to make the devices. So when we are applying the voltage and we want so there will be this much of this much of barrier will be there when we will apply the it will prevent the flow of the current. That's it. Okay, it will, because the electrons cannot go from this to this. When we give q phi b this much of the energy, to the electron, the V voltage, when we apply this much of voltage, then the electrons will transfer from the metal to the semiconductor. Okay, so this much of the energy will be required. But now, so this is an important thing in the device perspective. Okay, and another thing is, yeah, so how this barrier height will be there. So how this on what parameters this barrier height will be on will depend. So this is the metal for work function of the metal. The difference between the work function of the metal and the phi b is okay, and this chi is the electron affinity. Okay, this phi b will always be this. So it does not depend on the on doping. Okay, so it does not depend on the doping, because this is the material property. This is the electron affinity. Okay, electron affinity. So this does not depend on the material. This is the material property. This does not depend on the doping or anything. So both are the material properties. So if the work function of the, if we reduce the work function of the metal, so this barrier height will decrease. Okay, so it depends. And now let us find out the some other things, like what is this barrier height, or how much this is the depletion region, this WD, or we can say XD, whatever. There are different notations used in different books. So this is the depletion region width, we can directly say. So we will calculate the depletion region width. We won't go that much into the mathematics of the of this derivation. So we will simply we can calculate. Okay, there are very less parameters, less mathematics we need to use to find out this XD. Okay, so okay, let us suppose this is the depletion region width. So in the depletion region, so there are no mobile charges. Okay, though there are no mobile charges, the whole charge is because of the immobile ions, and because of the immobile ions there will be an field. So we are calculating that field first. Okay, from the Gauss law. So this is the Nd plus, this is the positive charge, this is the charge density. Okay, this is the charge density. And also we know metal is sink for the electrons. Metal can take as many as electrons and holes. Okay, so there won't be the charge density, this will be a delta function. Okay, so at this there will be a very thin sheet of the charges at the junction on the side of the metal. At this side there will be a sheet of the charges. Okay, because there is no we can say the charges will be at the interface only. Okay, so and another thing is so now we can calculate the electric field. From this we can calculate the electric field at dE by dx is equal to E Nd plus by epsilon naught. So this is the Gauss law, or the Poisson's equation, that we have already seen. Del 2V by del x square is equal to dE by dx is equal to from that we can calculate that. We have already seen in the PN junction. So from this we will just integrate on both the sides, so we can calculate the we can derive the equation for the electric field. Okay, so electric field is linearly decreasing at this from this point. So this is the electric field will be the, so when you will calculate, there will be an equation that will come out. Okay, so from the PN junction that you can see. So in PN junction, the electric field was like this. So this is the one-sided junction, or we can say the P plus plus N junction. Okay, highly doped P plus plus or N junction or PN junction. Okay, so or metal semiconductor junction. So the electric field will be highest at this point, and it will decrease linearly to the xt at this position. After this there is a neutral region. Okay, so and the bands are flat, so there is no electric field at this point. It should be 0, so it is linearly decreasing. Okay, so what is the maximum? And now from here we can calculate this voltage is a this phi or voltage, or we can say the potential. Okay, potential is quadratically dependence, because this is linear, then the potential must be a quadratic dependence, because dv by dx is equal to e. Okay, E is equal to dv by dx. From here we can calculate, we have the equation for E, and now we can calculate V. V is nothing but the potential. Okay, so from here we can calculate the potential, and phi b I is nothing but the difference between this and this. So okay, so this is the shortcut thing that we can calculate the phi bi, that it is nothing but how much bands are bending this at this position, so how much it is varying. Okay, so that variation will be nothing but the area under this triangle. Okay, the area, because what we are calculating from this integration, this integration we are calculating the area. Okay, we are calculating the area, we can directly calculate the area. So phi bi is equal to minus 1 by 2 E max divided E max into xd. So this is the area. Okay, the phi bi is nothing, the area of the under this triangle. So this is the built-in potential. Okay, from, and that will come with the in the form of xd, and from here we can calculate this barrier, this depletion region width. So depletion region width will come of this twice of epsilon I si phi bi divided by E and D plus. So phi bi from here, the phi bi, as we have already seen, this phi bi will be phi m minus phi s, metal, the work function of the metal minus work function of the semiconductor. From here we can calculate this depletion region width. Okay, now so what will happen when we apply the bias? So till here we have seen the equations in the equilibrium state, when this semiconductor is in the equilibrium state. Okay, so what will happen when when we apply a bias on the semiconductor? Okay, let us suppose that we are applying bias on the semiconductor, on the, like, we are forward biasing. So as we apply the voltage, so as we apply the forward bias, V is greater than 0. Okay, so what will happen is it will increase the electron energy. So at this side it is negative, at this side it is positive. So if we increase the voltage, this will go down, or we can say this will go up, because it will increase the electron energy. Okay, it will increase the electron energy. What will happen? The Fermi level will move up and along with the bands. Okay, so now electrons are electrons, the barrier, this QVBI is reduced to QVBI minus VA, the applied potential. Okay, so electrons, the hill, the height of the hill is reduced for the electrons, so electrons can move easily, and here they will find a kind of well, so they can easily jump over this hill here. Okay, they can easily jump, so a huge current will flow through the device when we apply a forward bias. Okay, so, and in this case when we apply forward bias, this depletion region width, will decrease. So the this depletion region width will be smaller, and the barrier height, this built-in potential height, will be lesser. But what will remain same is this built-in this barrier height in between the, when we electron will find the same barrier if it is moving from the metal to the semiconductor. Okay, but electrons from the metal, from the semiconductor, can move easily towards the metal. But okay, now what will happen if we apply a reverse bias? Reverse bias means that if we are applying a positive voltage here, so it will decrease the energy of the electrons this side, on the semiconductor side. So the Fermi level will move down along with the bends, so there will be a more bending at the junction. So there will be this depletion region width WD or the XD, this will increase. Okay, so and also the built-in potential, this potential height, barrier height will increase with QVBI minus VA, as minus VA means VA already has the sign as VA is less than 0. Okay, or we can say QVBI plus mode of VA. Okay, mode of VA. So this is the total barrier height that electrons will face while they are moving from the semiconductor to the metal. So they have to cross this much of the hill to go to the semiconductor side. Okay, to the metal side. So it will be very difficult for the electrons to cross this barrier. So there will be, the current will be lesser in amount. Okay, and now we will calculate the how much the current will be there in the PN junction, in the metal semiconductor junction, when it is forward biased and when it is the reverse biased, and how these barrier potentials, these barriers will this barrier height will affect the current. Okay, so there is an term thermionic emission. It is given by the thermionic emission. So let us suppose that this is a both here we are just supposing this is also a semiconductor, this is also a semiconductor, the electron at this level. So first we will assume that this side only. Okay, first we will assume this side only. So as our bends were like this. Okay, as our bends were the conduction band was like this. Okay, so what is the concentration of the electron? So what is the current will depend on the flux of the electrons, which is moving from this side to this side and from this side to this side. Okay, the flux of the electrons that are which are moving in between the junction. Okay, so it will depend on the flux, and it will depend on the what to say, the velocity. Okay, so the flux of the electrons, or flux of the electrons. Okay, so flux of the electrons will depend on the velocity of the electron at this position. Okay, velocity of electron. So at any point in a semiconductor, there will be a thermal velocity there will be a thermal velocity the electrons will have. Okay, so the flux will depend on the thermal velocity VTH. Okay, and number of electrons at this position. So what is the number of the electrons at this position, that we can calculate the difference between the conduction band and the Fermi level. Okay, which will be given by NC into exponential of minus of EC, minus of the difference between the conduction band and the Fermi level, okay, which will be given by this, okay. So which we can say NB naught here, NB naught, okay. So this the current will depend on the flux, and the flux will depend on the thermal velocity and the charge carrier density at this point, okay, at this point. So the current will be given by minus of E VTH into NB naught. So just we need to apply with the electron, the charge of the electron, okay. So where NB naught is given by this, NB naught is nothing but the concentration of the electrons at this point. So the equation will, the current equation will reduce the current from B to A, means at equilibrium the current will be equal. So whether it is going from this side to or from this side, so from B to A or from A to B, it will be equal to minus of E VTH into NC NB naught, or we can say this is the current, and we will put the replace this NB naught with the from the equation that we have, we can get it from the doping, okay. So so at as I have already said, at equilibrium the current will be equal. So whatever the current is from the semiconductor to the metal will equal to the current from the metal to the semiconductor, okay. So this is the current that is given at equilibrium from the metal to the semiconductor, and that same current will be flowing from the metal to the semiconductor, because the Fermi level is constant. So there will be current will be zero, okay. So the current should balance out at this position. And when there is a bias, okay, what will happen when there is a bias? So there will be a difference in between the Fermi levels, okay. So there will be difference in between the Fermi levels. So the concentration of the electrons at this position will be different, okay. So the concentration, okay, yeah. One thing I think I have missed is ACB. No, I haven't missed anything. So yeah, so the okay, the current which is flowing from B to A, first we will consider, okay, B to A, this semiconductor, okay, this semiconductor to the metal. So now the current will be different because of the concentration of the electrons at this position, which is given by ECB minus EFNB now, because it was initially at the previously it was the Fermi level was at this position, okay. Previously it was E of FNA, okay, that you can see both were at the same level. So it was EFNA, E of FNA, okay, they both were same. Now as we have applied bias, we have increased the energy of the electrons by this amount, okay. So this concentration of the electrons has changed from NB naught to NB. Now NB is equal to NCB exponential of ECB minus EFNB, okay. So the current will be now had changed to this now. And okay, also the current which is okay, initially here okay. Now, and another thing is, as we have previously seen, EFNB is equal to EFNA. So the current, there was already a current. How much electrons are flowing, whatever was the concentration of the electrons at this position, and they were flowing, Okay, so it was equal. Okay, so now the same thing we will apply here. So so what was the gap, what is the gap between these two? Okay, what is the gap in between these two? This gap will also dictate the current that is flowing from the metal to the semiconductor. Okay, this gap will dictate, so it will be given by this formula. uh, so it is a bit difficult, but it is not necessary for you to go through all the equation, but these are really very easy if you have you already understood the basics of the concentration of the electrons or concentration of the holes at any point. Okay, these are very very basic equation. So net current at this position, so net current will be whatever the current is flowing from the semiconductor to the metal minus the current flowing from the metal to the semiconductor. Okay, so this will be given by there is the difference between the current from both these will be the net current. Okay, so from here we can calculate the and one more thing, this is given by, okay, this EVTHNC, this term is given by AN star T square. So this AN star is nothing but this is a Richardson constant. Okay, this is the Richardson constant. This and this T square term comes from when we solve this the thermal energy. There will be a dependence of temperature kT by Q and there will be different 3 kBT and all. Okay, 3 by 2 kBT and all. And so now the net current will be given by the current between the difference between these two currents. Okay, so that we can calculate easily. Just need to get the difference, so it will come out, the final equation will be this minus of AN star T square exponential of minus of phi b divided by KT, this equation that you can see now. Okay, this equation. So this on what parameters? This depends on the Richardson constant. Okay, and the temperature and the barrier, this barrier height. Okay, this barrier height, and most importantly this will always be constant except at a constant temperature. This we can say at J naught, this will always be constant, and the further it is depending on the applied potential. Okay, what potential we are applying. Okay, so okay, this will depend on this thing. So if we increase the temperature, the current will increase obviously, and if we take it at different temperatures, so we can calculate the phi b from there. There are some methods. I don't know I have included, no, I haven't included that thing. So okay, so in this one, this J naught is nothing but whenever there is there is no potential applied across this, so there will be a flow of the current from the metal to semiconductor and semiconductor to metal, and that is this J naught, which is the leakage current, we can say. So at equilibrium it is balances out, and if we apply a negative potential, or we say the reverse bias, so this is the reverse bias current. Okay, because when we apply a reverse bias, these bands will go down and down. Okay, so there won't be any current which is flowing. There is no electrons which are flowing from the semiconductor to the metal, because this barrier height is too high, okay, for electrons to jump over this. But there will be current because of this barrier height, and which the current will always be equal to J naught. Okay, so electrons, the same electrons are flowing. Okay, the electrons are still flowing from the semiconductor, from the metal to the semiconductor. They will be constant throughout the process, whether we apply the forward bias or we apply the reverse bias. Okay, and that will be this will be constant always. And if we are applying the reverse bias, what will be the current will be the J naught in this case. Okay, so this J naught will be given by an star t square. It is approximately, an star is approximately equal to 120. Okay, so you can see other things also along that. And 120 per Kelvin square. And another thing is this phi b. This depends on the phi b. If we decrease the phi b, this the barrier height, or we can say the difference between the metal work function and the difference between the semiconductor work function, or not the exactly this, or actually this is given by chi, which is the electron affinity. Okay, if this difference comes down, or we say we decrease the work function of the metal, this phi b decreases and there will be a huge reverse current will flow. Okay, so as we can see, we have already seen in the PN junction, the characteristic IV characteristics looks like this. Okay, this is the like a huge current flows, and in this direction the current flows like this. This is the breakdown voltage, and this is this reverse current. This is the we say it leakage current. Okay, this leakage current will depend on the barrier height, temperature. Yeah, barrier height and the temperature. So in the PN junction, so this is the leakage current, this is the J naught, that is the reverse bias current. Okay, reverse bias current. So it depends on the doping concentration. Okay, it depends on the doping concentration of the if p type and the n type doping. Okay, so and that also depends on the on the band gap. Okay, or that we have already seen. So more the band gap, more the easy in PN junction, more the band gap, so this J naught is lesser. Okay, this is the band gap, and this is the phi b. This phi b is always less than the band gap. Okay, if the phi b is less than the band gap, so this current is the current related to this phi b is more. So here this J naught will always be more. Okay, so in a metal semiconductor junction, or if we are going for a diode, we want a diode kind of behavior, there will be very high leakage current. Not very high, we can say. There is the leakage current, the extent of the leakage current will be more than of that of the PN junction. So we need to see for what we say applications we are going to use this thing. Okay, so it depends. This can work for the application where we are not too much bother about the leakage current. Okay, so that's all in this Schottky barrier kind of PN junction, kind of the metal semiconductor junction. Okay, this was the metal semiconductor junction that come in the which was Schottky barrier. Schottky barrier means there is a barrier, the current can flow in the single direction. Okay, in a single direction when we apply the potential, and blocks the in the other direction. And now we will see the other thing. what will happen when we see, okay, in the Schottky ohmic contacts. Okay, so in ohmic contacts, so okay, so this was the metal Fermi work function of the metal. This is phi m, and what if, so this is the, okay, this is, okay, just a minute. This is the conduction band EC of the semiconductor, and this is the Fermi level EF of the semiconductor, and this is the EV. So here this semiconductor, the phi s, the work function of the semiconductor is higher. Phi s is greater than phi m. This is particularly for the n-type semiconductor. If this thing happens, if this is the case, so what will happen is the electrons, the energy of the electrons is more than the energy of the electrons in the semiconductor. Okay, so energy here is more than the energy in the semiconductor. So what will happen is the electrons, energy of the electrons will flow from the metal to the semiconductor to balance out the energies. Okay, so electrons will flow until the Fermi level will come, or will be aligned. Okay, these Fermi levels will be aligned. So at this point, at this junction, so there will be abundance of the electrons. Okay, so there will be abundance of electrons, and so what will happen is, okay, so there will be so how we can see that there is abundance of electrons, and that is given by the Fermi level. Fermi level will be more closer to the conduction band at this junction. Okay, so at this junction the Fermi level is, the bands will bend such that there will be more number of electrons. Okay, so at this junction there are more number of electrons than the far away from the junction. Okay, so bands will bend like this. So now there is no barrier for the electrons which are here. If we apply the potential, the electrons, there is no need for the electrons to jump any barrier. Okay, so the electrons, there will be very less kind of barrier, we can say. If that will also depend on this electron affinity and the metal junction. Okay, this work function of the metal. Okay, so so electrons can move easily back and forth at the junction. So there will be, so when we apply a potential, so electron, so there will be JV curve, the IV curve will be there is no barrier. So electrons can flow in this direction also and in this direction also. So the current can flow in this direction or in this direction. So there will be no barrier at this junction. Okay. So now what we have covered till now is the Schottky barrier, Schottky junction. If you have any doubt in this Schottky junction, you can ask me. So there are some things like ohmic contact and the Schottky barrier that we have covered. So now what we are going towards the next topic, that is the bipolar junction transistor. So first we can see what is a transistor. So in bipolar junction transistor or BJT, we always see as in every devices. Now it is replaced by the FETs, field effect transistors, most of the places. Okay, so what is a transistor? Transistor is nothing when if we can control, so in transistor, which is the transfer of the resistance. Okay, transfer resistance. Okay, so transfer resistance is like if we are applying voltage or current we are giving, so it is transferring the resistance to the other two terminals. Okay, so it is controlled. So what is the thing is the current between the two terminals, the terminal A and the terminal B, is controlled by the third terminal. Okay, the extent of the current flowing through the A and B is controlled by the third terminal. So this is so if the current can be 0, current can be 1 amp, 2 amp, 3 amp. So the current through this A and B is controlled, and this current is controlled by the this third terminal, which is, and this current is independent of the voltage applied in between A and B. Okay, this current is independent of the voltage when the third terminal we are the controlling the current with the third terminal. Okay, so we are transferring the resistance from this terminal C. We are applying the voltage at this terminal or current this terminal. We are transferring the resistance in between the A and B. So this is the transfer resistance. Okay. So there are two categories of the transistors which we can see. Now let me give you an example of the water flowing through a tap or something. So if this is the tap, this is a pipe. Okay, this is a pipe, and this current, this water, the extent of water flowing through the pipe is controlled by the valve. Okay, this is the valve which is controlling the flow of water through the pipe. Okay, so how much the valve I am opening, that will decide the extent of flow of the water through the pipe. Okay, so the flow in between the terminal A, or we can just say the source, or this is the A and this is B, the flow in between A and B is controlled by the third terminal. Okay, this is the gate we say. And another thing, the another type of the transistor, the category, another category is if this is a like this is the pipe. Okay, that let us say this is the pipe. So if we pull the pipe from the middle, okay, this is a kind of the flexible pipe, we are pulling the pipe from the middle, so it will increase the potential energy required to climb. It is more is the potential energy required for the water. It need to increase the potential energy. Okay, so how we are controlling, we are just pulling it up from the middle. Okay, so if we pull it down and we pull it up, we can control the flow of the water through this pipe. Okay, so this is the thing. So if this is shown here also, if we are just pulling it down from the middle, we can increase the flow. If we just can do the flat, we can increase the flow of the water. And if we just close the tap and open the tap, if we want to open the tap partially, we can also open. Okay, so partially opening means we are exactly controlling how much we want to flow the current. Okay, so now okay, so in between I have okay, let us see this type of the transistors. So where no, not this type, sorry, not this type. Let us see this type of transistor, which is the BJTs. Okay, so in BJTs what happens is, so the current in between A and B is controlled by the flow of the current at C. Okay, there is a small variation in the current at C terminal, that so that will this will affect the flow of the current in between A and B. Okay, so this is the current controlled device. Okay, we are giving the current at this point, and this is the current controlled transistor. Okay, and another thing is, this is a bipolar, means both electron and holes are flowing in this kind of the transistor. So actually I haven't done one thing. Let me introduce this card. Okay, let me check once if someone is there. Okay. Okay, so no, one more thing. So here, so this is a kind of NPN transistor. A transistor, this BJT is nothing but there are two PN junctions, back to back PN junctions. Okay, so this is P. Okay, now we will actually I have made the slides according to the NPN junction, NPN transistor. So this is N, this is P, this is N. Okay, so there are two PN junctions. One is this one is this one. Okay, there are two PN junctions. So we call it this one emitter, this one base, this one collector. Okay, so this is NPN. So if we make a Venn diagram for this one, so so let us say that this is the Fermi level. Okay, this is the EF, and in N region, this the conduction band is close to the, in N region, the conduction band. So okay, this is the let's say depletion region. This is the depletion region, this is the depletion region again. Okay, these two are the depletion region. So in this region the conduction band is close to the Fermi level, and in this region the conduction band is away from the Fermi level. Okay, so this is the region and this is the region. Okay, so okay, this is kind of this thing. Okay, yeah, this drawing is not that good. Okay, the fine. So this is the depletion region of this PN junction, NP junction we can say, and this is the depletion region of the PN junction of the in between the base and the collector. Okay, so here is the abundance of the electrons, here is the abundance of the electrons, but these electrons cannot flow because there is a barrier height. This is the barrier height. So there is excess of the holes. These holes cannot flow this direction because there is a barrier height. Okay, so now if we somehow we reduce this barrier height, so the electrons can flow from this side to that side. Okay, from the emitter side to the this collector side. Okay, so this is how we, if from this terminal, at this terminal, from the base terminal, we can reduce the height and we can flow the electrons from the emitter to the collector through the base. So the current will be decided from the base junction. Okay, now this is the Venn diagram that I have already made in the previous slide. So there are electrons. So this is the base region, this is the base region. So okay, so now okay, one more thing, actually I haven't these are the modes of the operation. Okay, these are the modes of operation. So we are making it active. Okay, active means we want some gain in the in the transistor. So we are looking for the for the amplification kind of thing. Okay, so BJTs are mostly used for the amplification of the amplification for the signal amplification in the mobile phones, in the radio also. Okay, so this in for this forward active region. So this emitter base junction, okay, emitter base junction should be forward biased, and the collector base junction should be reverse bias. Okay, so this junction should be forward bias and this junction should be reverse biased, as we have already seen in the PN junction. So when we forward bias this junction, so when we forward bias this junction, so this barrier height will be reduced. Okay, this barrier height will be reduced and the electrons can flow easily from the N side to the P side. Okay, and also the holes will also flow. Okay, holes will also flow. So this later we will see that these holes, the flow of the holes which are flowing, they are not coming from this side, but they are coming from the base. They are supplied from the base. Okay, so this is the current, this whole current is the base current, so which is very small and which is giving rise a huge current in this the collector, that huge collector current. Okay, so let us see if we are applying a reverse bias at this junction, which is the emitter base junction, reverse bias. So no, not the not reverse bias, sorry, we are forward biasing at the emitter base junction. So electrons can easily come from the this emitter side to the base. Okay, so now we have already applied the reverse bias at the base collector junction. So so at the base collector, so these electrons are the minority carriers in the P region of the base. Okay, these electrons are minority carriers. So whatever the minority carriers, they when at the junction, at the emitter base junction on the base side, so they will diffuse from the from this point towards the other, because of the concentration gradient. Okay, so as we have already seen in the PN junction, the minority carrier concentration will look like this. Okay, the minority carrier concentration will be exponentially decaying. Okay, so this minority carrier concentration will be exponentially decaying. Okay, so before they decay completely, or before, we don't want these to decay, because this decay is happening because of the recombination. Okay, so there is a recombination current that we will see later, and that recombination current is killing our device. Okay, so these we want we do not want to recombine these electrons, but we want these electrons to flow to the collector. Okay, so there is a very high potential or high electric field at this junction because of the reverse biasing of the base collector. So whatever holes come at this junction, they will be swept away at a very fast rate. Okay, so at this junction, the electrons, the concentration of the electrons will be kind of zero. Okay, the concentration of the electrons will be zero, the minority carrier concentration will be zero. So it will pull. Okay, so there will be a huge current flow as this barrier is as the electrons will come. Okay, sorry, as the electrons will go because of the forward biasing of this emitter base junction. So then they will be swept away. They will be swept away to the collector because of the reverse biasing. Okay, so now what we can see is, okay, this was the thing. This is the forward bias and this is the reverse bias. Because of that only the current is flowing. Okay, and there is also a hole current is also flowing because of this is forward bias. There is abundance of holes also, and which is flowing. But this whole current we want this as minimum as possible. Okay, we don't want the current, the whole current. Okay, we don't, because that is not contributing towards the this current, collector current. Okay, the whole current is from here only, that is not contributing to this current, this collector current. Okay, so these holes are supplied from the base junction, that base that we have connected. Okay, so these are supplied from the base, and these are not contributing to the collector current. So we want this current as less as possible. Okay, and so for that we can do some things, some device engineering, or not the device engineering, the doping of the in the p region, how much doped this p region should be, how much doped this n region should be. So from that we can reduce this current. Okay, reduce this current, and we can also play with the depletion region width in this region. Okay, so as we apply the reverse bias here, the depletion region width gets increased. So now initially this was the what's say the base region. Okay, so from this was the base region, which is not depleted, but which is the neutral base region, we can say neutral base region. But when we apply a reverse bias, high reverse bias, what will happen is this base region will be shrinked. Okay, so electrons in this region have to spend less time. Okay, so less time, so the recombination probability will also be reduced as we apply the reverse bias in this junction. Okay, so the current will be more, we can say the collector current will be more, because the recombination current will be reduced. Okay, another thing is we will come in the next slide again. So these are the profiles. So we are in this case we are applying. So in this one, this is the forward bias. So these are the carrier concentrations. Okay, yeah, these are the carrier concentrations. So once in the PN junction, one thing we have read is the short base region and long region. So the minority carrier concentration there, this is the base minority carrier concentration, that is the this is the p region. So n naught was there, so delta n or np naught. Okay, np naught is nothing but the minority electron concentration on the p side. So this is the delta n was decaying like this. Okay, for the long base region, this was the this exponential decay was for the long base region. But for the short base region, so if the region is not sufficient, region is ending till here only. Okay, if the region is ending at here only, so this is the base region, we can say. So the electron decay will be linear. Okay, will be the profile of the excess minority carrier concentration. This is the minority carrier concentration, excess minority carrier concentration will be linear. Okay, so this is what they have shown here. Okay, the excess minority carrier concentration, this is the base region, this is the p region. Okay, so this is the excess minority carrier concentration. Okay, and also this is the whole concentration will be negligible at this point. So negligible in the sense it is shown 0. Okay, this electron concentration is also falling to 0 because this is the reverse bias junction. Okay, reverse bias junction, so everything at this junction, at this point, will be swept away. Every hole at this junction will be swept away. So that's why the hole concentration is 0 and the electron concentration is 0 at this junction. Okay. Now there are several components of the current that which are flowing through the BJT. Okay, so there will be this the current will be because of the electrons at this point towards this junction. Okay, so this is the electron current. So okay, this is the electron current, IEN. Okay, so there will be holes also. Holes are flowing from here at this point to this point. Okay, so there will be flowing of from the P region to the N region, because we have forward biased this. Okay, if we are forward biasing, there will be flow of the holes from the P to the N region. Okay, because we are decreasing the depletion region width, we are decreasing the potential barrier. Okay, so if we are decreasing the barrier for the electrons as well as for the holes, so both the currents will flow. Okay, electrons will flow from the N region to the P region, and holes will flow from the P region to the N region, but the direction of the current will be the same, because if the electrons are flowing in this direction, but the current will be in this direction. So there is shown this figure I took from the Google images. So the current will be in the opposite direction, and these directions are shown as the flow of the electrons and the flow of the holes. So the hole current will be also in this direction, electron current will also be in this direction. Okay, so this current component IEN, so this IEN is also reducing here. These are the flow of the electrons. These are reducing because of the recombination, that the profile that we have seen, that the excess carrier concentration. Okay, that profile is like this. Okay, this is because of the recombination. The recombination current is there. Okay, the electron there will be recombination also, and there will be a swept away of the electrons at this junction. At this junction, when we reverse bias it, at this junction there will be a swept away of the electrons. Okay, that this current, which is because of the drift of the electrons at this junction, the drift. Okay, this drift current is nothing but that IC. This is what we are interested in. Okay, and what we don't want is the recombination. And there is one more thing, this recombination of the holes, there is where are the holes are coming from, because at this junction this is the minority carrier, the holes are very less, but the holes are coming in this junction. From where are they are coming? The holes, they are coming with, they are supplied from the base of the battery that we have connected. Okay, so this is the recombination current, and also the holes which are going from P junction to the N, from the P side to the N side, they are also supplied by this battery. Okay, so there are two things that we do not want in the BJT. One is this recombination current. This recombination current we don't want, and another thing we don't want is the flow of holes. Okay, this current we do not want. We want we just want this as least as possible. We cannot reduce, but okay, just okay, we how we can reduce these things. Okay, the recombination current we can reduce by decreasing the width of this base region. So if this region will be small, okay, if this region is small, then there will be very less chances of the recombination of the electrons in this region, because there are excess holes. There is no no absence of the holes, or there is no scarcity of the holes, but there is a scarcity of the electrons that which are coming from the n side. Okay, and how let me make the Venn diagram here, so you will easily get this thing. So I am just making a okay, so this is the n region. Okay, I'm sorry, I am not okay. So this is the n region. Okay, let us say this is the thing. Okay, so initially at equilibrium. Okay, initially at equilibrium, this base region, this region, the what to okay, this is the depletion region in the reverse bias was smaller, but as we have reverse biased it, this depletion region width is increased. Okay, this depletion region width is increasing, and that depends how much it is going towards the base side. Okay, how much it is going towards the this collector side. So that depends on the doping, extent of the doping. If this is highly doped, n plus doped, okay, if this region, this is collector region, if this collector region is highly doped, what will happen is the extent of the depletion region in the collector region will be lesser. Okay, if this is less doped, this p region is less doped, okay, the extent of this depletion region will be more. Okay, say this is the depletion region, this is the depletion region, this the extent of the depletion region in the p region or in the base region will be more if it is lightly doped. Okay, now again this is n plus plus doped. Okay, so this is the, so electrons, as soon as the electron come at this point, it will be swept away. Okay, so we have reduced the effective base region by reverse biasing it. Okay, by reverse biasing it. And another thing is, okay, and another thing is okay, just a minute. Okay, so another thing is, so this is highly doped. Okay, if this is highly doped and this is lightly doped, so what we have already seen is there was a the current due to the whole current, we wanted this as least as possible. Okay, how we can reduce this current is by lightly doping this p region and highly doping this n region. Okay, this is n plus plus indicates very high doping. Okay, n plus plus highly doping, this is lightly doped as compared to n plus plus, and this is the least doping p. P plus plus, P plus, P plus and P plus plus are kind of the highly doped. Okay, so from these two we can reduce the current, this whole current as well as the recombination in this base region. Okay, yes, and also when we make the PN junction, we can also reduce the width of the p region if we can keep it as least as possible, so that it can work for us. We cannot go too less, because if we go too less, if we reverse bias it, it will be completely reverse biased, so there will be a current without turning it on. By just reverse biasing this one, we can turn on the device, so that will be not good. Okay, so we do not want our this p region a very small and not very large, for so that it just a optimum we need. Okay, so and these are I think this is the last slide. Okay, so these are the performance parameters. Okay, so I see okay, the base transport factor B. Okay, base transport factor. So in the base transport factor, okay, base transport factor is the how much the current is recombining. We are losing the current in the recombination. Okay, the base transport factor. So as we have seen, the current will be this is the our Venn diagram. Okay, whatever. Okay, so and there is a recombination in this region. Okay, when we reverse bias it, we reverse biased it, and when we forward bias it, so there is a recombination current in this region. So and another thing is there is a there are two currents. One is the recombination, we are losing this IEN. Okay, wait another this is not the recombination. Okay, there are two currents. One is the because of the flow of the holes, flow of the electrons, IEN, and another is because of the flow of the holes, that is IEP. Okay, there are two currents that are flowing in at the emitter base junction. Okay, so this current, what is the how much current is because of the electrons? Okay, how much current is because of the electrons, which is contributing to the which is contributing for the device. Okay, so this IEN uh, the total that IE is nothing but IE is equal to IEN plus IEP. Okay, but what we want is the most of the current, that is the emitter current, should be because of the electrons. Okay, in NPN. So this is the unwanted current. So how much extent of this IEN is there in uh, in our junction, in our this BJT. So this that is contributing that to the IC. Okay, that is contributing to the IC. So this is given by the base transport factor. Okay, this is given by the base transport, because there is, because of the in the base there is whole current also that we want to minimize. Okay, so another thing is emitter injection efficiency. Now comes the how much the extent of the this electron current is there in the total emitter current. Okay, so this emitter injection efficiency is given by the contribution of the electron current, the ratio of the contribution of the electron current to the total emitter current. The total emitter current is given by the IEN plus IEP. IEP is the because of the holes. Okay, because of the holes, this current. Okay, and this IEN, this IEN plus IEP, these two currents we are adding. Okay, these two currents we are adding to get the total emitter current IE. Okay, now and another is the current transfer ratio. So how much our current IC divided by IE. Okay, this is the current transfer ratio. So we are giving some current at the emitter junction and how much it is at the collector junction. Okay, so it is given by okay, IC by IE. So IC we can write B into IEN. Okay, B into IEN, which is IEN plus IEP. Okay, now from here IEN divided by IEN plus IEP, which we can convert to gamma E. Okay, which is the emitter injection efficiency. So this is nothing but the B of gamma E, B into gamma E. Okay, which is given by the emitter injection efficiency multiplied by base transport factor. Okay, so this is the current transfer ratio or the this which is given by the alpha. So now finally we come on the current gain. Okay, current gain is given by the alpha divided by 1 minus alpha, or we can IEN divided by IE, or let me check once. Okay, I have IC divided by IP. Okay, current gain is given by alpha, or this is the beta. Okay, current gain beta is given by current collector current IC divided by IB. Okay, IB, yeah, the base current. Okay, base current is the combination of the recombination current plus the base emitter junction current, that is holes are flowing. Okay, so from here we can this can be alpha divided by 1 minus alpha. Okay, so and if you have any doubt in this region, in this one, so you can ask me. There are some other performance. These are the 4 performance parameters only, so we can rigorously also calculate these for there are different type of junctions. If we replace this with the metal, what will happen with, if we replace this with metal, if we replace this junction with metal, what will happen? Or we change the work function of the metal, and then we, if this is making a Schottky junction, if this is making a Schottky junction, and if we put both metal, one is Schottky and one is Schottky barrier, one is the ohmic contact. So there are several combinations that we can see from the equations that we have covered in the PN junction. One is the PN junction and another in the Schottky barrier. So in Schottky barrier, we have calculated the current in between the metal and the semiconductor through the thermionic emission. Okay, that can be applied here. How much the current is going, how much is the reverse current, how much is the forward current, that we can apply here and we can easily calculate. Okay, and there are yeah, actually this was a bit faster. So but you can ask if you have any doubt in this region, in this particular case. So because if you ask the question, then I can tell you more in more depth, but sometimes I might miss some things that may be important, because I don't know, sometimes I don't remember whether uh, which things I have missed and which things I don't have missed. Okay, so if what will happen if we do the both the forward biasing, both the reverse biasing, what will happen in these cases? Okay, so if we at in this case if we both if we reverse bias at the both the junction, this is reverse bias, this is reverse bias, what will happen? The this will go down, this will go down, there will be no current flowing. Okay, so and there will be kind of zero current flowing, because there are 2 PN junction back to back. Okay, so there won't be any current flow. This is a very less current will be flowing, so that 2 will be the reverse current, and will be very less. And another thing is okay, there are very less things that I have told in these transistors. So and this was thermionic emission, so which was a bit more confusing actually, moreover say. So it is not that much required that I have told you, but just you just need to remember this equation, how this is this J naught, and how it is depending on the voltage that we are applying at the terminals. Okay, in the forward region or in the backward, in forward bias and in the reverse bias. Okay, and this is the equation that is given in the PN junction. Okay, how it is different from the PN junction, how this metal-semiconductor junction is different, because in the PN junction diode, there the reverse leakage, the leakage current can be controlled, and that can be very less. Okay, but in metal-semiconductor junction, the reverse leakage current, the leakage current is very high. Okay, so which is in microamps, we can say microamps, and in this case this is in nanoamps or lesser. In in picoamps also. Okay, so but in this case it is very high, so we cannot so there will always be a loss. Leakage current is loss, nothing. Leakage current is loss, so it will be very less, very lossy kind of device. Very we just want to turn it off, but it is still the current is flowing. The current is flowing, it is consuming the energy. Okay, but in this case the current is very less, it is consuming less energy. Okay, so when if we say what how much the current when we put our laptop or put our phone, mobile phone, in a just we turn off the screen, how much the current is flowing in the backward of the of a transistor, or if in the leakage current, that dictates how long our battery will be, how much energy it is consuming. If the leakage current is more, our even we are not using our cell phone, still it is consuming the energy, so which is not required. Okay, which is not required, and this is uh, uh, dying out, our battery is dying out. So that's why it is this leakage current is very important. Okay, and all these thing is based on this diagram. This is the main thing, this is the main thing. Okay, so that we have started. Okay, so that's all for today, and if you have any question you can ask right now, or you can write in the comment box also.